Hello student, good morning. I am Dr.A.K.Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing states of matter part 2, that is the liquid and solid states. Already I have finished gaseous state. I am reviewing the chapter. Then gaseous state, after finishing gaseous state, now I have started reviewing liquid and solid states. Then liquid state yesterday I finished. Now I will start solid state. Then first point today I am going to discuss difference between crystalline solid and an amorphous solid. Difference between crystalline solid and an amorphous solid. Amorphous solid is also called pseudo-solids. Pseudo, pseudo-solids. Then differences I am telling you. Crystalline solid and amorphous solid. First point I am discussing crystalline solid. The constituent particles are arranged in a regular fashion, having short range as well as long range. In crystalline solid, the constituent particles, every solids are made from some particles. Particles may be cation and anion. Okay. Then in crystalline solid, the constituent particles are arranged in a regular fashion, having short range as well as long range order. And in amorphous solid, the constituent particles are not arranged in regular fashion. They may be at the most short range order. Generally, it will be at the most short range order, but in crystalline solid, both are possible. First, regular fashion, short range as well as long range in crystalline solid, but in amorphous, all are, you can say, reverse way. Here it is, you can say, no arranged any. It is not arranged in regular fashion, means irregular. Not arranged in regular fashion. And second, there may be at the most short range order. Their arrangement may be of short range, not long range. Second point of difference is they have sharp melting point. Crystalline solid have sharp melting point like 200, 300, 350, 315, 300.5, like that way. Sharp, fixed. They have sharp melting point. But here amorphous, they melt over a range of temperature, means not sharp, not fixed. They melt, amorphous solid melt over a range of temperature. This is the second difference. Third difference, crystalline solids are anisotropic, and amorphous solids, they are isotropic. Iso means same. Means arrangement you will see, you will find that they are arranged in a some special fashion. But here in crystalline solid they are anisotropic. Okay, not like, they are not same, but here amorphous they are isotropic, but in crystalline it is anisotropic. Now next fourth point of difference is that is, they undergo clean cleavage, breaking. It can break, clean cleavage. They undergo a clean cleavage. Cleavage means breaking, to break. And amorphous, they undergo an irregular cut, not regular, irregular cut. If you try to cut from some angle, it will cut from the other angle. Okay, that is an irregular cut. Then in crystalline solid, they undergo clean cleavage. Here in crystalline, wherever you want to cut, only from there it will cut. But here, amorphous, it will cut from other side, not from that. They undergo an irregular cut. And one more point of difference is, that is the examples I am telling you. All elements here, examples of crystalline solid, then all elements, whatever you know, all elements or compounds are crystalline solid, like NaCl, KCl, calcium chloride, magnesium chloride, all elements and compounds are examples of crystalline solid. But here, amorphous solid example, what is examples of amorphous solid? Then few examples are there. Rubber, glass, polymers. These are the examples of amorphous solid. Question is asked that example of amorphous solid. Then here examples are rubber, glass, polymers, etc. Now I am going to discuss next point, types of crystalline solid. Types of crystalline solids. Depending upon the constituent particles, there are 4 types of crystalline solids. First solid is ionic. Second solid is covalent. Third solid is molecular. And fourth is metallic. Correct? Then depending upon the constituent particles, there are 4 types of crystalline solids. All four what I discussed are crystalline solid. There are 4 types. First type I told you, ionic solid. Second, covalent solid. Third, molecular solid. Fourth, metallic solid. Then for each I am telling you little more. Ionic solid. What are their constituent particles? For ionic, then positive and negative ion. Ionic solids are made from positive and negative ions. And what are the binding force? Which forces are binding positive and negative ions? Then it is electronic forces of attraction. Electrostatic force of attraction. Remember, positive and negative ions are bounded by electrostatic forces of attraction. What are the examples of ionic solid? Then sodium chloride, potassium chloride, potassium nitrate, lithium chloride, barium chloride, barium carbonate, all are example of all salt are examples of ionic solid. Now come to the second type, covalent solid. Covalent solid. Then here what are the constituent particles? Then here no positive, no negative. No positive ion, no negative ion. Then what is this? Atoms. Atoms. Here constituent particles are atoms. Atoms are the constituent particles of covalent solid. And what type of bonds are there in covalent? Then it is well known, covalent bonds. Covalent bonds are present in covalent solid. What are the examples of covalent solids? Then it's you can say popular examples are diamond, silicon, quartz. These are the examples of covalent solid. Now, what are the molecular solid? Molecular solid. Then here example I will tell you, but here just to understand what are the constituent of molecular solid. Then very simple way, molecules. For the covalent, atom was the example. Atom was the constituent. But for molecular solid, molecules are constituent particles. And what are the binding forces? Main binding force. Then van der Waals forces. Van der Waals forces. Correct? Van der Waals forces are present in molecular solid. And what is the example of molecular solid? Solid, molecular solid is there. Then its example is solid carbon dioxide, dry ice. What you are telling? Dry ice, solid carbon dioxide. Second example is iodine solid, I2 solid. Third example is sulfur, S8. Sulfur, 8 atoms are present in 1 molecule of sulfur. In 1 molecule of sulfur, 8 atoms are attached. That's why it is known as S8. Then example I told you, solid CO2, iodine solid means I2, S8, etc. Now metallic solid. Metallic solid, what are the constituent particles? Then here remember positive ions, but not negative ions. Positive ions and mobile electrons. This is the difference. In ionic it was positive ion and negative ion, but here ions are positive. Positive ions, and in the place of negative ions, here it is electrons. Electron is negatively charged, you know. Then mobile electrons. One side positive ion, other side mobile ions. Mobile electrons. And their number is very large. C of electron you can tell. SEA, C of electrons. Very large number of electrons will be there. But this large number of electrons means large number of negative charge. That's why it is balanced by positive ions. Then metallic solids means constituent particles are positive ions and mobile electrons. Okay, this is the important. And what are the forces binding the you can say metallic solid? Main binding force is metallic bond. And what are the examples of metallic solid? Then it is examples are very common. You are knowing all metals and some alloys. All metals, iron, copper, aluminum, whatever you know, all. And some alloys. Now next term I am going to discuss, that is the Bragg's equation. Bragg equations, question is asked and a student will not answer. Okay, Bragg's equation, BRAGGS, Bragg's equation. What is a Bragg's equation? You remember 2d sine theta is equal to n lambda, small n lambda. Remember always this relation, equation, 2d sine theta, that is equal to n lambda. Now I will tell terms involved. Then here d means what? D is equal to distance between successive atomic planes. Actually many planes will be there. What are the distance between the planes? Atomic plane, you remember, many planes are possible in substance. Okay, then between the two planes. What is the distance? Distance between successive atomic planes. Successive atomic planes. That is a small d. Correct? D is equal to distance between successive atomic planes. Many planes are there. Then successive means between the two you can consider. Suppose 3 layers are there. Then 1 and 2, then 2 and 3, 3 and 4, like that way. Then any layer you can consider between first and 2, between the 2 layers. Then what is the distance? That is a small d. And what is the theta? You know, well known that theta is the angle. Theta is equal to angle of the incident X-rays with the crystal surface. Actually, crystal has many layers, I told you, atomic layers. Then if X-rays, for the measurement purpose, light is passed through the crystals. Correct? Crystals are in layer form. Then which type of rays radiation is passed? And that radiation is X-rays. X-rays is passed. Then what is the wavelength of X-rays? Not wavelength. Wavelength also is there, but at what angle it is passing? At what angle? That is the angle of incident. Angle of incident of X-rays with the crystal surface. That is called theta. Theta. That's why here it is written sin theta. Okay. Theta is the angle of incident of X-rays with the crystal surface. And lambda, that is the wavelength of X-rays. Wavelength of X-rays means radiation. And a small n is equal to what? N may be 1, n may be 2, n may be 3. And 4, n may be 1, value may be 1, 2, 3, 4, etc. Called the order of diffraction maxima. This small n is equal to maybe n, maybe 1, maybe 2, maybe 3. And these n is called, these 1, 2 and 3 are called order of diffraction maxima. Here you should note down important things. The diffracted beam makes an angle of 2 theta with the direction of incident beam. If incident beam is theta, then diffracted beam will be 2 theta, double. Okay, here you must remember the diffracted beam. Incident beam is theta, then diffracted beam makes an angle of 2 theta with the direction of incident beam. Now next term I am going to discuss, that is the crystal lattice. Crystal lattice. A regular arrangement of what is actually crystal lattice? Then in a simple way you think, just to imagine that you have taken any things in, or you can just suppose that any solid which is in you can see in atom form, that things you consider dot 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 dot, like that way you think. Dot 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 means atoms, or maybe cation, maybe anion. Okay, that you think that in air it is there. Air, just to think. Air, why I am telling? Because 3 dimension you have to consider. Means length, breadth, height. Then just to suppose in air you will find clearly what is the height, what is the breadth, okay, length, breadth, height. 3, that is called 3 dimension. That always you consider whenever you are studying solid state, then you have to consider what I am telling you that way. That it is in a space, that is called a space. Here I am telling you that is in a, that is called a space. I am not interested in telling about the gases in our air, means in a space. There you can see all three, length, breadth, height very clearly you can see. Then always you imagine things or crystal of any solid. In a space you consider three-dimensional space where you can see length, height, breadth or depth, whatever, height or depth, okay, opposite of both, anyone. Then in a space means now you understand, just like that space only, a sky. But here you consider only in upside, not on earth, upside, not on land, upside you consider, so that you can see very clearly length, breadth, height. Always you think like that. If you are studying this solid state, then you have to consider this way. Then it will be clear. You can understand all angles, you can understand. Otherwise, it will be difficult. It is very difficult to make that diagram. In paper, if you will make that diagram, you will get confused. Then for understanding purpose, you can either take you can say that models already it is made in that structure you can see, and that should be transparent. Otherwise again it will be clear, transparent. How all things are arranged, you can all atoms are how arranged, how all ions are, how they are arranged, what are their angles, correct, angles, how they are making angles with each other, all things should be clear. That type of transparent model you require, okay. Or you can buy I can say sometimes you will get for atom a small sphere will be there, that will represent atom, and a string will be there that you can fit it, that will tell about the bond, correct. And then different type of to show the different type of atoms, different color, a sphere will be there, a sphere will be of different color. That different color means different atoms. Sometimes a string that will be also different to show the different bond, correct. Then this I told you because in solid state, until you will consider, you will imagine, you can't understand. Or you can understand only by seeing the models. A model must be transparent, or you can just make it, arrange it. If many spheres are there, in that sphere hole will be there, so that you can insert the string, correct. In two sphere you can string, then a string will tell about the bond, and two sphere may be the same, means two atoms may be the same or different, then different color sphere you can say join. Then this type of things you have to consider. Then now I am telling about the crystal lattice. Lattice, why the word lattice? You should not be confused. Don't think it is very big things. It is just like a structure you can understand. A structure may be complicated or ordinary, or sometimes very simple, sometimes little difficult, sometimes more difficult, sometimes complicated, okay. But it is just like a structure that you keep in mind. Then what is actually crystal lattice? It is very important for the concept point of view. Then a regular arrangement of the constituent particles of a crystal in three-dimensional space is called crystal lattice or a space lattice, correct. That is a regular arrangement of the particles. Simple way. Particles means maybe atoms, ions. Then a regular, how atoms or ions are arranged in a regular way in a crystal, how it is arranged. That arrangement of particles of a crystal in three-dimensional space means x-axis, y-axis, z-axis means length, breadth, height. How much length is there, how much breadth is there, how much height is there. In that way, how it is arranged. That arrangement of the constituent particles of a crystal in three-dimensional space is called crystal lattice. Correct? Or a space lattice. Lattice means simple, you can understand, a regular arrangement of constituent particles of a crystal in three-dimensional space. Now, what is a unit cell? Unit cell. Then it is very, you can say, easy to understand. Suppose you have taken one cube. One cube you consider a small cube, or in a simple way you can understand one bricks, correct? One brick, and there are, suppose 1000 bricks. Then 1000 bricks you can arrange in different way, in a square way also. You can make a square also, you can arrange, keep it in a square form, rectangular form, correct? Triangular form, you can keep in many ways. But whatever be, these square or rectangular or triangular, you have kept 1000 bricks in three shapes. But all are made from the one brick only, one bricks. Then one brick is just like a unit cell. Then one brick is just like a unit cell, because only from that arrangement of many bricks you form the crystal, big crystal. Then like that way, unit cell is a, you can say, one part. Okay, the smallest three-dimensional portion. In brick you see length, breadth, height is there. Or in cube, if you are consider cube, then also length, breadth, height is there. Then the smallest three-dimensional portion of the space lattice, which when repeated over and again in different direction, produces the complete space lattice. Then that smallest three-dimensional portion of the space, that is called unit cell. Again I am telling you, unit cell is the smallest three-dimensional portion of the space lattice, which when repeated over and again in different directions produces the complete space lattice, and this is called unit cell. Understood? This is called unit cell. Unit cell is the smallest three-dimensional portion. You remember, smallest three-dimensional portion of the space lattice, which when repeated over and again in different direction produces the complete space lattice. Correct? And then this smallest three-dimensional portion of the space is called unit cell. What are the types of unit cells? Then now I will brief you. Okay, I am revising. Sorry, I have already discussed in details in the 11th and 12th. That when I was teaching that time, I have discussed in details. Here I am reviewing, and so I will just only important points I will discuss. Then how many types of unit cells are there? Just like I have given example, brick example, that is one type. cube example, that's the second type. In cube, length, breadth, height, all things will be equal. But in bricks, length is different, breadth is different, height is different. Correct? In that sense, I am telling you types of unit cells. Okay. Then first type is simple. Simple. That is a simple unit cell. Here the particles are present only on the corners. If you see the crystal, then you will find particles are present only on the corners. Suppose a square was there. Then a square shape you just to keep in mind. Then every corner you can think one atom is there. Means 4 atoms. Each corner one atom. Correct? Upside 4. Cube, you are considering a square form. Correct? A square, length, breadth, height, all sides will be equal. 4 sides. Then in cube I am talking about. Then in cube, 4 upside and 4 down. Correct? All corner 1. All corner 1. Okay. Then that is called simple unit cell. Here in simple unit cell, particles are present only on the corners. Only on the corner, whatever type will be there, but they will be only on the corners. Okay, when the particles are present only on the corners, that is called simple types of unit cells. There are actually 4 types. And simple type I told you. Now face centered. By name it is clear. Here, in addition to the particles on the corners, there is one particle present on the center of every face. As for example, cube is there. Then every corner it is there. Particles are there at every corner. Correct? And additionally, on each face at the center, one particle will be there. And suppose 6 faces there in a cube. In cube, how many faces are there? Left, right, 1, or direction wise you can understand. North, south, east, west, up, down. Total 6 faces. North side, south side, east side, west side, up side, down side. 6 faces. Then on each face at the center, one particle will be there on each face. This is additional, on corner will be there. And after that, this is extra. Here, in addition to the particles on the corners, there is one particle present on the center of every face. Then this type of can say cell is called face-centered unit cell. Face-centered unit cell. Third type is end face-centered. End face-centered. Okay, by name it is clear. End. First end, second end, There will be 2 end. First end, second end. Beginning and last. Then here in that sense you can think. Here, in addition to the particles on the corners, there is one particle in the center of 2 opposite faces. In the center of 2 opposite faces, as for example, north and south face you are considering, then between these 2 at the center, between the north and south at the center, one particle will be there. This is extra. On the corner it will be there. On the corner it will be there. In addition to this, that between in the center of opposite, okay, in addition to the particles on the corners, there is one particle in the center of two opposite faces. Now third type of unit cell I am telling you. Then third type I already told you, that is the N face centered. That is in addition to the particles on the corners, there is one particle in the center of two opposite faces. Now last type, body centered. Body centered. Okay. Here, in addition to the particles on the corners, there is one particle present within the body of the unit cell. Correct? Again I am telling you, body centered. Body centered. Here, in addition to the particles on the corners, there is one particle present within the body of the unit cell. Correct? Cube is there. Then in the center, one particle will be there for the entire body in the center. Correct? That is called body centered. Then here, in addition to the particles on the corners, there is one particle present within the body of the unit cell. Then I have discussed 4 types of unit cells. Okay. Now this okay, now today I am stopping only here, because types of crystal system I have to discuss. This will take more time. Okay. Then next class I will discuss types of crystal system and their axial ratios and angles and unit cells. Correct? Here you have to understand and you have to remember also. Then now other many points are there. I will discuss in the next class. Thank you.